Okay, hello everyone. Let's start. It's my great pleasure to introduce Dr. Shay Moran, Professor of the Technion. Shay has been a leading figure in theoretical machine learning ever since I heard about his work when he was a student at the Technion. At that time, it was advised by Yehudai and Shmilka, having some kind of theory, more crowd theory, complexity, and so on. But it's not the really big open problem that was posed by Manfred Darmus and was remained open for 2 decades about how compression implies loadability and vice versa. And he solved it pretty much by himself at that time. Everyone was very impressed with the learning theory community, which I was and still am a member of. So that's when I heard about him. Then I kind of didn't think about him for a few years. Then he arrived to Princeton, and by some karma, we met, and he became a postdoc in the Google lab, and he was there for 3 years. This was the best time of the Google lab, at least from my perspective. And he, at that time, of course, professionally, he had all the best papers on solving problems in differential privacy, and later in SVMs and VC dimension, and so on. So numerous best paper awards in the postdoc call. But the best thing for me was personally such a fantastic guy that it was the best time, at least for me in Princeton, when he had coffee every day in Princeton, and maybe I don't know if that's the best introduction, Shay, but that was at least for me the best thing about him. So it's a great pleasure. It's fantastic researcher, fantastic person, and if you have the time to talk to him, I highly recommend it. Amazing problem solver, an amazing person. So please, let's welcome Shay.
Yes, I remember during COVID, we started working on a robotic project just to retain the access to the Google office and enjoy our coffee. Okay. Yeah, so it's wonderful to visit Princeton again. We had really wonderful 3 years here with my family. And we miss it dearly. And it's really exciting to visit Princeton and to see old friends. Okay, so yeah, so today I'll present joint work with our subset of our Google team in the Google Research Tel Aviv. Mark is also a member of this team, but not a author. Yes, and it is about differentially private planar algebra. And I don't care if we don't reach all the technical details and the main result even. Like, please ask questions. Like, if I'm not assuming anyone is familiar with the definition of differential privacy, and maybe it's not clear why is it the right definition. So I'm happy to hear your thoughts and to discuss it, and you can challenge the definition. Yeah, okay. Okay, so let's start with some, right? So maybe this question is kind of easy. So why do we care? Why should we care about privacy preserving algorithms? And when I teach a class in differential privacy, I usually have this toy example that serves to intuitively present the definition. So imagine that you go to your family doctor, and they tell you about this initiative where they're going to train a deep neural doctor. So imagine it's like a GPT, like a language model that will later be used all over the world, including in places that have no access to proper medical service. And then the person can chat with this model, and they can write about the problem, maybe upload some data, some medical data, and be diagnosed and get good medical care. And your family doctor asks you, so of course, in order to train such a model, we need a lot of data, including medical data, and they ask you to share your data. And of course, I think most of us will agree that this is a worthy cause, and maybe you would like to help to contribute our data. But at the same time, we might also be afraid of some terrible event E that will happen as a result of us contributing the data, right? So maybe someone later will interact with this LLM, with this GPT, and as a result will prompt it in various ways and find out sensitive information about you. Right, so on the one hand, we want to contribute our data to help science. I don't know what, but on the other hand, we are afraid that as a result, because we share sensitive information, someone will later use this system in adversarial ways and find out private stuff about us. Okay, so let's keep this example in mind. We will later use it also to give the formal definition of differential privacy. Okay. So this is just a third example, but of course, in real life, in practice, privacy is a real concern in social networks, right? So when you log in Facebook, you have your feed, and what you see on your feed is a result of how much time you pause and on some post, and so they really use private information about you to dictate the post that the algorithm showed you. Recommendation systems, right? Yelp, so kind of restaurants that you recommend you is based on restaurants that you visit, so also private information. Navigation apps, right? So this is also, they know essentially where you go. So they can collect private information about you. So this is a real issue. And our group, so we study, so we do theoretical, we're theoreticians. So we study two basic questions. The first question is a little bit like computability, right? So which tasks at all can be performed while protecting private data, even if, say, we don't even care about computational concerns, right? So just to satisfy, you will see soon the definition, just to satisfy the definition of privacy, like which tasks can be performed, even if we don't care about running time. And the second question, which is a refinement of this first one, is what is the cost of privacy in terms of various resources. And in this talk, we will discuss linear algebraic tasks. Okay. So let's begin now with the definition of differential privacy. So what you can see, this is a gold standard in the area of privacy. It's used by so the United States Census is performed by algorithms that are at least inspired by differential privacy. The reason I say inspired will clarify later. And GDPR, the European Union, recognizes differential privacy as one of the kosher methods to protect data. And Google, with parabolic law, yeah. So it's really a gold standard in the area. So let's now define it. By the way, Iridi Nu is here. She was the person who actually defined it with cognition. And so, okay, so let's go back to our example from before, right? So I'll just remind you, you go to your family doctor, they tell you about this exciting initiative to train a GPT-10, which is going to diagnose people all over the world and provide medical services. And they ask you to share your data, and on the one hand, you want to share your data, but you're also afraid of some event E, say that someone will later prompt this GPT in various ways and find out personal information about you. Okay, so you're worried. You tell your medical doctor this worry that you have. And then if the deep neural doctor was trained using or subject to differential privacy, then they could pacify you, they could relax you, the doctor could relax you by saying that don't worry. The likelihood of this event that you are so scared of will not be affected by your decision. What does it mean? So imagine we pause the world and we now consider two threads, two different continuations of the world. In one of them, you give your data. So you say yes to the doctor and you give your data. And in the other one, you don't. But all else is the same. So the rest of the data that the algorithm is trained on is going to be exactly the same. And now we push play on both threads of reality, and we ask, like what is the likelihood, what is the probability that this event E that you're afraid of will happen, right? So we look at formally a set of all GPTs that are trained with your data that are bad, that someone can prompt them later and find out your data, and the set of all GPTs that were trained. So, right, so there's this set of all GPTs that are bad for you. We look what is the probability of this event in the first case and in the second case. And the definition of differential privacy in a quantitative way, which I will soon describe, tells you that any event E, including this particular event you're afraid of, has the same, roughly the same likelihood in both scenarios. Make sense? Okay, so let's now give the formal definition. I don't know why it keeps. Okay, so here is a technical relation. So let epsilon and delta be two numbers, two positive numbers, small, like they're small. So we say that x and y, any two real numbers, x and y, can be very large also, are equal up to epsilon delta if we have these two inequalities. So x is at most e to the epsilon times y plus delta, and vice versa. Y is at most e to the epsilon times x plus delta. And if we remember that e to the epsilon is roughly 1 plus epsilon, what it means is that x and y are the same up to an affine transformation that is almost identity. Right? There is an affine transformation that is very close to identity that maps x to y and vice versa. And now we say that two distributions, right? So now we have some domain x. X is going to be the set of all GPTs or outputs of the algorithm. We have some domain x, and we say that two distributions are epsilon delta indistinguishable if for every event E, these two numbers, the probability of the event under P, the probability of the event under Q, are epsilon delta indistinguishable. Okay? Now, what is differential privacy? So, A is going to be the algorithm that we want to define when it's differentially private or not. So, the part of A that we need is just the mapping that it induces, right? In order to define privacy. So, A is a mapping that gets a sequence of data points, Z1 up to Zn. Each data point is private information. So, Di could be your input, your medical data. And it outputs some output, right? So the GPT, for instance, the model. So it's a mapping from sequences of size M, for some M, to some abstract output space. And notice that if we have a randomized algorithm, so the mapping is also a randomized mapping, right? In order to specify the actual output, we also need to specify the randomness of the algorithm. So the way we think about randomized mappings is as deterministic mappings that takes an input sequence of size M and output a distribution over the outputs. Right, so that's how we think about randomized nets. Okay, so we just have a randomized net, which is mapping from sequences of size m to distributions over outputs. And now we'll say that such a randomized map or algorithm is epsilon delta differentially private if for every pair of neighboring inputs, right? So in one case, you gave your data, in another case, someone else did, but all else remained the same. So two pairs of neighboring inputs, or two sequences of length that disagree on a single position. If we look at the distributions over outputs, A of S and A of S prime, these two distributions, they should be indistinguishable. Right, so going back to our example, let's say A is the training algorithm of this GPT. So we have here two distributions over models, over neural networks with, I don't know, billion parameters. It's a distribution because the algorithm is randomized. And these two distributions are indistinguishable if you just change the input in one location, running set. Make sense? Yes.
So the samples you need to distinguish between A of S and A of S prime is like poly 1 over epsilon?
So you're asking, now you're describing a scenario, let's say you can now sample from the distribution over outputs, right?
Yeah.
So you train the GPT again and again and again and again and again many times. And you do the same here maybe. Yeah. And you ask how many samples will I need in order to be able to distinguish them. So, yes, we can, yeah, right. So I think it relates to what they call in privacy composition. This is exactly this kind of process that you described, that you interact with a different algorithm again and again, and you measure how privacy deteriorates or how the ability to distinguish improves with more samples. And yeah, this is a well-studied. But if you just have one sample, then you have this epsilon delta indistinguishability, right? And you can ask how epsilon delta deteriorates as you get more and more.
Yeah.
But the definition itself is clear, right? So for every event, so this is the distinguishable. For every event, the probability of this event here and there are the same up to this small affine map, and epsilon delta determines how your ability to distinguish between them.
I was gonna say, maybe here's a different way to phrase Rohit's question.
Mhm.
So this is a multiplicative guarantee on probability of events.
Both.
And I think his
Both epsilon
both are
delta.
tough, right? And I think Rohit's question is about what's the additive total variation distance guarantee. And it seems like naively it only will be epsilon.
No, so that, okay, let's go back to the definition. So we have here both a multiplicative guarantee
Yes.
and an additive guarantee.
Sure, yeah. But
Right, so if we plug in epsilon equals 0, we simply say that these two distributions are delta apart in total variation. And if you plug in delta equals 0, then you get something like KL divergence, but maybe in the worst case, or the worst case event. So KL divergence, you take an average with respect to one of the distributions of exactly this epsilon.
So your points were well spread. I mean, if your distribution was relatively well spread, the epsilon, you'll basically never see the epsilon. You would have to, if all the point, if the support is like size n, then and delta is so small you never see it. Then the difference between 1 over n and 1 plus epsilon over n. It would take a lot of things to see this, not simply scaling that.
Yeah, I mean, this is like an indistinguishability thing, right? If you just have delta, then you could distinguish probability delta. We have here this epsilon to also take care of very small events, right? So it could be that my bad event has probability 1 over 10,000. I wanted to not multiply. So epsilon takes care of this. So it says, the likelihood the event can multiply by at most the epsilon. And delta, yeah, so delta, that's maybe a technical point. Delta we should really think about as a negligible function of m number of samples. Right, so delta is like much less than any polynomial in 1 over m.
So should I just
So this definition actually applies to all events, right? Including
Yeah.
events that might have probability under, let's say, P or Q about half. In that case, the additive difference between the probabilities would be epsilon, which means that the total variation distance between
Yes.
the two distributions can be as large as epsilon.
Yes, yes,
So,
yes.
so therefore, like 1 over epsilon samples would in principle be enough to distinguish.
Yes, for such events, yes, for such like heavy events.
So you really think about you're trying to control very rare events. That's the only.
Yes, yes, yes. So actually, the first definition was with delta equals 0. Okay, this is called pure differential privacy. And then really what it says to you is, whatever event you're afraid of, the likelihood will multiply by at most into the epsilon, 1 plus epsilon. And then a negligible delta was introduced to circumvent impossibility results. Be able to perform more tasks. I think everything that we discussed today really requires delta larger than 0. Okay. And okay, so now maybe I'll tell you why I claim that the application of differential privacy in doing the census in the US is only inspired by privacy. And it's because they used epsilon equals to 18.9. 18.9, yeah. So at least in the last time. So it's really right. So if the probability of the event you're afraid of will only multiply by e to the 19 roughly. If you show your data.
Bigger than 1 seems weird. Epsilon bigger than 1 seems weird.
That's how they.
All the probabilities are really, really small.
But it's still, I mean, we make fun of it, but really the definition is really worst case, right? So it applies to all events. But still, like the algorithms that were developed in this framework, they add noise in a much more principled way than previous algorithms that were sort of ad hoc. Anyways, okay. So good. So we know the definition. And now I'm going to discuss our work. So we study constraint satisfaction problems, right? So imagine you have, what is a constraint satisfaction problem? So you have a bunch of constraints. Each constraint is a subset of solutions. And you want to find a solution that belongs to all subsets in the intersection of all constraints. In particular, solving linear equations is a constraint satisfaction problem. Each equation gives you a constraint of all solutions that satisfy the equation. And you want some that satisfies all of them. Similarly, linear programming, linear inequalities is a CSP, is a constraint satisfaction problem. And here we think about each constraint as a private data point, right? So if I give you two systems of linear equations that disagree on one equation, they are considered neighbors, and we want to be stable with respect to such input. Okay? So what does it even mean to have a differentially private solver for such constraint satisfaction problem? So maybe the first definition that comes to mind is, okay, we just want a differentially private algorithm that for any sequence of constraints, it outputs a solution, and this mapping, this randomized mapping between inputs and outputs is DP stable, is differentially private. And when let's say probability 0.9, it will output a correct solution. Let's assume the system is satisfied, otherwise it's NP hard. So let's assume. So is this possible? Can I hope to have a differentially private algorithm with this property that for any feasible system with probability 0.9 will output a correct solution? Is it possible to achieve this? Is it possible to satisfy the definition of differential privacy for such maps?
I think probably not because like for this simple equation, like the how is probability 0.9 of 1x, one specific x, but then if you change only very slightly, then the system of value is completely different, which is completely different for the 0.9 probability of a different x.
Yeah, it sounds in the right direction, but it's much easier, right? The mere existence of a solution is an unstable property, right? I can take just the ith equality, replace it by 0 equal 1. Right, so this system is is satisfiable. This system is not satisfiable, but these are two neighboring systems. So I cannot hope that with probability 0.9 I will output a solution to feasible systems and at the same time satisfy the definition of differential privacy with non-trivial parameters. Because an adversary can come and just change one equation, make it non-feasible. And therefore, if my algorithm was differentially private, even for the non-feasible solution, it would still output a solution of the feasible thing with probability 0.9 times e to the epsilon minus epsilon. Okay?
So here each equation is like held by one person. That's
Yes,
what it is.
yes. Yes, you could, yeah. Okay, so the solution existence is unstable, so so we cannot hope for the naive definition to be satisfied by stable algorithms. So we need to take a compromise, and the compromise that we made, and also other people, is that okay, so we assume that the input system is satisfiable, and now we want this DP mapping, this DP algorithm that outputs a solution that satisfies as many equations as possible. Right, so we allow it to not satisfy some of the constraints, but it should satisfy as many as possible. And how many, like what is the minimum number of equations you must not satisfy if you want to be differentially private? This is an open question that I will soon, and it's even open in the information theoretical setting, meaning you just want a stable randomized mapping that for any system outputs a solution in a DP way. It can even be non-efficient or even non-computable, like really just the mathematical map from inputs to outputs should be stable. Like what is the minimum number of equations you must use? I will discuss it soon. But first, let me tell you our result in this context. So what we do is a little bit more than just solving, like finding a solution. We do what they call in this area, we publish a synthetic system. What does it mean? For our algorithm, it gets the input system, linear system, and it outputs another linear system. This mapping between the input system and the output system is differentially private. So you really think about this output system as some sort of synthetic data. It's not real data, but it's representative of the input data. And in what sense does it represent the input data? In the following sense. So every solution to the input system solves the output system. Namely, we never lose solutions. We can add some solutions, but we never lose solutions. And every solution that we add solves all, but at most, d squared over epsilon is the privacy parameter of the input equations, where d here is, I wrote it as number of variables, but it's really the dimension of the span of the equations. Okay, so yes.
Yeah. So if n is sufficiently large compared to n, then you could apply like this recent CSP classification results and get a stable mapping like that.
I don't know which results you're referring to.
So there are like the sequence of papers for the last 2-3 years that show that if you take any CSP,
Okay.
if n is sufficiently large compared to n, then you can approximate
So m is number of equations and d
Oh, sorry.
m is like number of constraints.
Yeah, number of constraints
It's sufficiently larger
compared to number of variables.
That's it.
Then you can take any instance of the CSP and construct a weighted sparsifier
For instance,
with the property that for every assignment, the sparsified instance has a value which is 1 plus minus epsilon of the true value.
So this is only over real space.
No,
1 plus minus epsilon with the true value.
fractions.
You satisfy. Okay.
Or like really unsatisfied.
Okay, and this is differential private also.
No, it's just a stable, I'm saying like this seems like a way to get a stable mapping like yours.
You still don't know if it's stable under.
In the right sense. So,
Also, it's not clear to me, we're used to the epsilon fraction of the equation. What is this d squared over epsilon as a fraction of the equation?
so it's an additive, not a fraction.
Additive,
Oh.
the d squared is, what is it compared to m?
Yeah, so this applies for any m and d, but of course it's only non-trivial when m is larger than d squared over epsilon. Otherwise, you just these all equations.
And m can be d cubed, and then this is like a sublinear.
Right.
additive.
Right. And you might ask, like, when do we care about? Okay, so when do we care about such cases when m number of constraints is much larger than number of variables? You will see soon. It's very important for the linear programming, but it's also inevitable. So here is an open question. So again, what is the minimal number of unsatisfied equations, even information theoretically? So there is no way to get below d over epsilon, and we get d squared over epsilon. This is information theoretic, this lower bound, or even non-efficient, non-computable algorithms must miss this as well. That is so many solutions, so many equations. And this is an efficient upper bound. And it's additive, so it's a little bit different. But still, even if so, I think it's also interesting to study multiplicative quantities. But I wonder whether your falsifier, or not yours, whatever falsifier that you discussed,
Yes.
I'll try with DP. So and it's only for linear equations or for
For any case. For every constraint satisfaction problem.
any, like just
Yeah, so it's important though that you need so for every predicate, let's say it's a d-ary predicate in the way you're writing, then there is some fixed value depending on the predicate, such that you need m which is n to that value. So you might need the number of constraints to be
sound
like,
interesting.
Yeah.
Here, the locality, it's not local d squared, or is it?
What do you mean?
Meaning the entire, how many variables in total we have, d? Every
Yes.
constraint looks potentially at all of them.
So it could be local. So as I said, it could. So D can be relaxed to be the affine, the dimension of the affine span of the equations. So you could have many variables, but all dimensions span d-dimensional space, and the algorithm does not need to know this even to work. So in some sense, it's more local, but I don't think it applies to sparse equations because they can span a very large space, even if you have sparse equations.
So is the conjecture known for existential result or?
No. I'll be interested even in just non-efficient. Okay. So now let me tell you quickly about the linear programming, and then I'll discuss some anecdotes about proof and algorithms. So here we don't have this synthetic thing. We actually solve the LP. The algorithm is based on ellipsoid that I might discuss a little bit more later. And here we output a solution X that satisfies all inequalities. So here we are only over real space. Right? So real space satisfies all inequalities, but at most some polynomial, which is very hard to compute, of in the dimension, so number of variables, bit complexity, how many bits you need to describe each number, and the privacy parameters. And basically, this is the first efficient algorithm for this problem. And also here, it's open. What is the minimal number of unsatisfied constraints? Recently, so this paper that I'm presenting now was presented not presented because of the war, but was supposed to be presented in talk in June. And 1 month later, there's already an improvement the number of unsatisfied, and they actually computed both our polynomials and a better one. Yes, that.
So, if you're working on the real numbers, in some sense, the natural notion of violation here would be that to satisfy the constraints upwards.
Right.
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 I guess you have a reason to do the differential practice, why you feel about it.
You could also study this notion, it's natural, and yeah. In some sense, it's easier.
It's much easier, then you can, I think there are any methods that will give you.
There are some, so some of the previous work, there are a couple of works.
That one based algorithm.
Ours is also perceptron based, so for the same.
So is that notion studied? It's not
Yeah, it's studied.
So why do you do this topic?
I mean, so one thing which we developed is like learning an algorithm for linear classifier, and this required this kind of. So that's how we came to this problem.
I think the learning classifier in the 0-1 sense, otherwise you would.
In the 0-1. Yeah, if you have a convex loss, then you can just, so for stochastic convex optimization, if you want to do different properties, so at least the information theoretical is sort of solved, right? You just take a cover of the space, and it's still, there's a lot of work at how to do gradient descent based algorithms and differential property optimally, but yeah, so this is in the, yeah. Okay. Now I want to tell you about two sort of highlights that I found curious about this work. Okay, so the first highlight has to do with duality. Let me explain what I mean by duality. So one form of duality, so we have two natural ways of representing polytopes in RD. One way is, I just give you the vertices of the polytop and I take the convex half of the vertices. This defines the polytop. Another way is I give you a bunch of linear inequalities corresponding to the faces of the polytop. You look at the intersection of all these half spaces. These are two dual ways to represent polytopes in RD. We also have the same kind of duality for linear equations, right? So we have two natural ways to represent affine subspaces. So think about linear subspaces. One is I just give you a basis and you take all affine combinations. Another is I give you a bunch of linear equalities and you look at the solution space. Right? So an affine space is just a translation of a linear space of a subspace, and every solution space to a linear system is an affine space. There is also a dual way. And now, you can consider the basic computational problem of feasibility, polytopes or affine subspaces, and think about it from both perspectives, the dual and the prima, right? So we are very familiar with the feasibility problem of polytopes that are represented by half-spaces. This is just linear programming. We are also very familiar with the feasibility problem of affine subspaces when represented by linear equations. This is just the, solving a linear system, what Gauss studied. We could also ask it in the dual form, right? So consider the problem where I give you as an input a polyhedra, which is represented by its vertices, and I ask you whether to output a point in this polyhedra. It's not a very exciting problem, right? You can just output the first, right? You can just output the first vertex. Yeah, so, and you can do the same thing for I give you an affine subspace, I give you a basis of it, and ask you to output a point in this affine subspace. Again, it's not very exciting. You can just output the first thing. So no, it's not a surprise that you don't see a lot of literature about these variants, but you do have a lot of literature about this kind of formulation. It turns out that once you require your mapping to be differentially private, this becomes highly non-trivial. Right, so I give you now a bunch of points, x1 up to xn, and ask you to just output a point in the convex hull. This becomes highly non-trivial. And the only way we know, so we also give the first algorithm for this problem. And the only way we can solve it is via an equivalence. So there is some sort of equivalence that we prove also between these two. Right, so there are efficient reductions that preserve privacy in both directions. And this is how we solve this. So we first do the linear programming in a differentially private way, which is based on a perception algorithm by sorry?
Wasn't that?
No. A variant, an efficient variant of it, which gets log 1 over margin by that margin. Impala, thank you. Yes, so that's one interesting thing, right? So that you have these very simple problems that become highly non-trivial with privacy. And yeah, so the reduction, the equivalence between these two problems is done by ellipsoid kind of algorithm. And here it is done by a very nice combinatorial process that I might tell you a bit at the end if we'll have time, which we call peeling basis. This was sort of the key, one of the key technical ideas in this work. Second highlight I would like to discuss is weak versus strong polynomial time computation. Okay, so linear programming is in P. Okay, so this is known since the 70s. However, all efficient algorithms are weakly polynomial. So what do I mean by weakly polynomial? So it means that the runtime, the complexity scales with the bit complexity of the input. Maybe what we would have wanted is an algorithm that you count how many basic operations it does, like multiplication, addition, division, how many basic arithmetic operations it does, and you want that the number of such operations will only depend on the number of variables and the number of constraints, inequalities. So this would be a strongly polynomial time algorithm. So Gaussian elimination, where we solve linear equations, is a strongly polynomial algorithm. Right? You diagonalize the matrix. Each step you perform order of n products and subtraction. And then once you can implement each such addition and subtraction multiplication efficiently, you get a polynomial time algorithm immediately. And there is a major open problem in this area: are there strong polytime LP solvers? Can we find that? So, for example, simplex is sort of an algorithm that that his access to the input is only by these basic operations, and you could ask, can you find an update rule such that the number of overall iterations will be polynomial in the input? But we don't know that. So this is a big open problem, and it turns out that our work combined with previous works resolves it for differentially private algorithms. In what sense? So our contribution is to show that you can solve LPs with weak polynomial algorithms. So as I said, the algorithm is based on ellipsoid and it depends on the bit complexity, as you would expect. However, at the same time, so nobody really interpreted it like this, but it's just an interpretation of previous results, is that you cannot have strong polynomial time algorithms for linear programming, even in one dimension, and even if you forget about efficiency, you just talk about the information theoretical existence of a stable map that takes constraints to solutions, the size of the input of such a map must scale with the bit complexity of its numbers. So the impossibility result is sort of information theoretical, and you can interpret it in this way. And yeah, this is even in 1D. So in 1D linear program is really simple, right? You get a bunch of points on the line. You want to output something between, let's say, the minimum and the maximum. So even this problem is in some sense only weak polynomial is sort of yes.
Can you just clarify what you mean by weak versus strong for an information theoretic? Well, like you said, forget about runtime, that's information theoretic thing about mapping. What does weak versus strong mean?
So, so you want a differential private algorithm. So let's look at this problem that we decided, right? You get a bunch of points on the real line, and you want to output a point between the minimum and the maximum. We can do it, but the number of points you need to, the input size has to be at least log star the bit complexity of the number. So this implies that you cannot solve that. And maybe one thing I forgot to say, one open question which I think is nice. Yeah, so here, so how many constraints must you not satisfy if you want to retain privacy for linear programming? So here, the information theoretical lower bound, it's related to this result we just discussed, is log star of bit complexity. So here there is a huge gap, right? We have a polynomial in the upper bound, but it could be that, you know, it's really nothing. Like the dependence on the bit complexity is just log star. You can essentially satisfy all inequalities up to something that only depends on the dimension.
Can you use some intuition?
Why log star comes up? So no, but what I can say is that even in the one-dimensional problem, right? So imagine you just have n points and you want to output a point between the minimum and the maximum in a different private way. So already there, so with the lower bound log star comes there, and it arises from some Ramsey argument, right? So basically you take any algorithm that solves it, and then you color the input space in a way that the coloring depends on the algorithm. And this gives you a homogenic space of inputs where the algorithm is very predictable, and there you can attack it. There you can show that privacy must be breached if the algorithm is differentially private. So it's, I don't know if it counts as intuition, but that's how we do it.
Maybe it's useful to say the algorithmic side, like.
The algorithmic side is also known, but how do you reach the log star? He asked, what, you want to say something?
There's somewhat better intuition at least we heard about. It's like you take your domain and you build somehow a binary tree out of it, and you match to like a path of a binary tree, and then just continually recurse this. You keep moving to log, blah, 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 etc. And you stop the recursion and set the log star.
Right.
That's somehow. You're right, I'm lower about this.
Yeah. Yeah. So in the one-dimensional case, we will. So we also have. Let's continue playing. We also have an upper bound, which is log star. Like as long as the dimension is constant, then the number of you can also efficiently only miss log star with constraints. And in the one-dimensional case, this is how you do it. But why you cannot do it is, yeah. So that I don't have good intuition. Just.
But the point is that the log star, that something as a function of b has to.
Yes, yes, exactly. And the Ramsey argument is not too complicated. It's but it's yeah. But in contrast with other lower bounds, that like in information theory and complexity theory, this one is not based on a minimax argument. So it's not like you find one Hull distribution is going to be Hull for all algorithms. You really take the algorithm, you look at the code, you color the domain, and you find a subset of the input which is particularly Hull for that algorithm. It's not like a Yao minimax kind of thing that you find a hard distribution of the input which is Hull for all algorithms. Okay, I think I'm done. How much time do I have? Maybe I'll tell you about the filling basis if I have a little bit more time. Or not? 10 minutes we have? Okay, so I'll just tell you a little bit about this, this nice, maybe I have it. Yeah, so one very nice combinatorial process that we needed to study, and this is sort of the engine behind the linear system solver. It's the following process. So imagine you have a sequence of vectors, v1 up to vn and rb. Okay, now we're going to build this sequence. So what do we do in each iteration? So in each iteration, so we start with an empty list. And then, we go over the vectors one by one, and we always add a vector to the list if it's independent of the set of vectors accumulated so far. Okay, so let's see all vectors are non-zero. So in the first iteration, I'm going to collect v1 because it's independent empties of what collected so far. And then I'm going to check whether v2 is say like a scalar times v1, and if not, I add it, and then you go to v3, and you always check whether the next vector is linearly independent of what accumulated so far. And in this way, if you think about it, in each iteration we collect a basis to the span of the current list, right? And right, so at each time we collect an independent set, and each independent set we put it in a bucket, which is the name of the bucket is the space that it spans. Right, so in the first iteration, I will just collect a basis to the span of these vectors, and then we put it in the bucket whose name is the space spanned by v1 up to vn. And then in the next iteration, we collect another independent set, and we will put it, maybe it will still be a basis to the same space, and we will put it in the same bucket, or maybe it will be a spanning set for a subspace, and then we'll put it in a new bucket. So how many buckets are we going to see in total in this process? How many different buckets? How many different spaces are we going to encounter which are spanned? Right, so notice that the buckets form a chain, right? So the first bucket is the span of v1 up to vn. The second bucket is subspace of it. Third bucket is a subspace of the second bucket. So we have a chain of spaces, and the longest chain of spaces of dimension d is at most d, right?
Manage to spend the entire idea. What's the next step?
Yeah, so let's say I collected v1, v5, I don't know, some d vectors in the first iteration.
Spend the entire.
This span the entire space. Now look at the span of the remaining thing. In the next iteration, you will
Think the vectors from now on.
those that were not removed in the first iteration. So in each iteration, I start from the beginning.
Oh, those you didn't pick.
Those you picked, you erase.
Those I picked, I erase them. Those you picked. Exactly. So in each iteration, I do one pass. In each iteration, I do one pass. I pick a basis to the span, I put them in the bucket, and then I do another pass, and so on.
So the size we hold.
Exactly. Right, so that's what I said. So the sequence of buckets is a chain. The largest space and the subspace of it, and therefore Because you know,
We have the same space again and again, like mostly.
You-
most of the
exactly.
time you will have
and
this out of the deep.
that's very important, actually, that's why it's so stable, this process is crucial for us. Right, so, and for the vector spaces, we know that if U is subspace of V and they both have the same dimension, then they're equal. That's why the number of buckets is at most D. Okay? And moreover, so this process is really cool. So it's super stable, this process. If you now imagine you run this process, but you remove one of the vectors, right? So you take V1 up to Vn, now you remove V17, and you run the same process again, and then you ask yourself, which buckets will you get and what will be the count? It's highly stable, right? Like you will get almost the same count. There will be at most 2 buckets with different counts, and even then the differences will be at most 1. And so this process is very, very, and this is not immediate to see. You need to meditate a little bit. But
Means stable in the sense that I can remove the first
in the
vector.
sense that I said, so take V1 up to Vn, take another sequence which is V1 up to Vn, but now remove one of the vectors, and now apply the same process. So you go over the vectors, and then you see the subspaces that you got and the counts.
Yeah. On the level of subspaces, it seems, yeah.
That's the same. So you will have
And the level of what's in each bucket on the level of the vectors, clearly it can have been like.
Of
completely changed.
course, but you will get the same count with the so yeah. So as I said, it will be at most in 2 buckets there will be a difference, and the difference is at most by 1, like number of bases you put it. Okay, so if there are any questions, I'm happy to take. I can tell you about some other stuff if you want, or we can just go. Okay, so
Okay, let's thank the speaker.
thanks. That's